So, okay friends, welcome to this class of plate tectonics, and we are discussing the destructive plate margins. In the last class, we are talking about the seismic system or the seismic structure of this subducting plate and the surrounding. And today, we will talk about the gravity anomaly and the thermal structure of the subduction zone, and particularly the subducting slab. So, that means what is gravity anomaly and what is thermal structure? So, gravity, that means it is the pull of something, that means a heavy material and it is pulling to another material, that is the come under the domain of gravity. So, here the gravity anomaly, that means if you can remember, we are talking about this gravity anomaly in terms of a free air anomaly and this that is called this Booger anomaly. So, probably you know that, otherwise in detail about this free air system and this Booger system, what is Booger anomaly and free air anomaly, that will be taught in geophysics, particularly in gravity prospecting. And at this stage you just know it, where there is a mass deficit or there is a mass excess. So, that can be expressed in terms of gravity anomaly. So, here why this gravity anomaly occurs? Because in the subduction zone, we have somewhere addition of mass, somewhere we have mass deficit. For example, suppose we are subducting a slab, that means the slab was earlier not there. We are transporting it from some other places and they are putting it here. So, that means we are adding the mass here. And we have a trench. The trench, that means it is a gap, it is a highly depressed area, there is gap, there is nothing, only sediment and water. So, that means here mass is less, mass deficit is there. Then we have accretionary prism, the volcanoes. The volcanoes, they are adding the mass to the system. We have back arc basin, fore arc basins, they are full of sediments. So, that means I want to say, in the subduction zone we have different features, somewhere there is mass added and somewhere there is less mass. So, due to this imbalance of mass, the gravity comes into the picture. Where there is high mass is there or mass added mass is there, then we are getting the positive free air anomaly, and where there is mass deficit, we are getting negative free air anomaly. So, Booger, we are talking about the Booger density anomaly. Depending upon the density contrast, we talk about this Booger anomaly or so. So, let us talk about this gravity anomalies in the subduction zone. Here, once we are going from this way to this trench, here is the trench, here this is the trench and this is the plate subducting, and here it is the bulge. This is the bulge and this is subducting down. So, here the flexural bulge, it elevates the high density mantle rock down of the lithosphere to the seaward side of the trench, and it is marked by positive gravity anomaly. Because you see, this plate is moving down and due to this compression it is bulging out. Once it is bulging out, that means here we are bulging the system, that means we are allowing this mantle to move up. That means mantle, it is a high density material. So, that means we have a high density material near to the surface. So, that is why we are adding this mass here. Earlier this mass was not existing here, it was somewhere lower level, and once we are flexing this, we are bulging it, this mass is coming to this near to the surface. So, that is why we are adding some mass here, that is why it is a positive gravity anomaly is there. The trench and the accretionary prism are typified by negative gravity anomaly. Here we have a trench, that means it is a depressed area and it is filled with the sediment. The sediments, they are of low density material, sediment and water is filled with there. So, that means we have low density material where occurring here. So, that is why it is representing the negative gravity anomaly or negative free air anomalies. Island arc, it is marked by large positive anomaly. We have island arc here, here the volcanoes are, that means we are adding the mass here. So, once we are adding the mass, again we have positive free anomaly or gravity anomaly. So, that means depending upon this deficit and excess of mass along the subduction zone, the gravity anomaly varies. So, free air gravity anomaly over the Andes is positive, averaging about plus 50 milligal over 4 kilometer high plateau. So, now you see this is the Peru-Chile trench, and this is the profile is taken along across this Peru-Chile trench, and here is the Chile trench which is subducting down. This is the plate which is this is Nazca plate which is subducting down around this or beneath the South American plate. So, you see this trench is representing negative free air anomaly, and this is the Andes mountain, and at the Andes mountain this side it is positive anomaly because we have these island arc systems, and this is the plateau of this Andes, it is represented near about constant, and once you are coming to this edge, again we have positive system because this is represented by this low density material of this Andes here. So, below we have high density material and here we have low density material. So, high is near to the surface, that is why we have positive system. So, even stronger anomalies up to plus 100 milligal are seen over the east and west boundaries of this Andes, and this is largely due to the age effect of this low density Andean rock. So, we know this Andean rock is here and we have this shield or this lithosphere shield area, or it is the cratonic area here, and this side we are putting the low density rock. So, that means below we have high density material and this is the low density material. So, that is why we are getting two positive horns in two opposite direction, that means to the end and to the beginning of this Andes mountain. And this continental crust is about 65 kilometer thick beneath the Andes mountain, give rise the negative Booger anomaly. Negative Booger anomaly, Booger is a density anomaly. So, Booger talk about the density. The continental crust, it is of granitic to granodiorite composition. So, that is a low density minerals. So, that is why it is giving large negative Booger anomaly. And a strong positive free air anomaly of about plus 70 milligal lies between the Andes and the shoreline of the Pacific. This is due to this subduction of the Nazca plate. So, the subduction of this plate, that means we are inserting a mass here, which this mass was earlier not existing, it was somewhere in this way. So, that means we are adding a mass here, that is why we are getting a positive anomaly here. So, this following changes takes place once the subducting plate is going down. First is it is heated up. So, once it is heating up, its density should decrease. So, this decrease in density, it is compensated by the suppression by this press due to pressure. So, once you are going down, the temperature is increasing, the pressure increasing. So, due to increasing of temperature, the material may convert to low density material. However, as the pressure is increasing, so this density difference is compensated. So, there is a positive density contrast between the subducting lithosphere and the surrounding material. So, that means once this plate is going to sufficient distance, there are phase changes. If you remember our earlier class, we are talking about this dehydration of this material, it is converting to eclogite, serpentine it is converting to olivine, and further it is converting to spinel. So, that means gradually we are getting high density materials here, and that is why this part of this plate, it becomes so dense and so heavy that it is denser than the surrounding material. So, once it becomes denser than the surrounding mantle, so it will bend down, it will just hang it like this. So, that is why petrological changes accompanying the subduction result in mass excess, and this mass excess it is expressed here. Peridotite in the upper lithosphere changes phase from plagioclase type to the higher density garnet type. When oceanic crust is subducted below 30 to 80 kilometer, basalt changes to eclogite, which has a higher density, and that is the then the upper mantle rock that we are talking about. This becomes high density and compared to the surrounding asthenospheric system. So, these effects combine to produce the positive free air anomaly, because we have less dense rock here and we have high density rock here. That is why it is creating positive free air anomalies there. So, the sediment flowing in the trench have low density, and the mass deficiency of this water and sediment in the trench cause a stronger negative free air anomaly, which is parallel to the trench, and its amplitude is greater than about minus 250 milligal. If you see here, whatever this Peruthili trench, it is represented through this gravity profile. Here this trench is about minus 250 milligal, and these are representing the positive and some of this negative. So, that means wherever there is mass deficit, there is negative, and where there is mass excess, there is positive gravity anomaly has been expressed across the subduction zone system. Now, let us talk about the thermal structure of the subducting slab. So, this plate is undergoing, it is the oceanic lithosphere which is undergoing, having a sediment layer at the top and the petrolatic layer at the bottom. It is serpentinized, it is fractured. So, that means at the subduction zone, a cold, rigid, fractured, partly serpentinized basaltic crust sandwiched between sediment layer at the top and peridotite mantle layer at the bottom descends into the asthenosphere at a variable angle and speed. So, this statement, it says everything about this oceanic lithosphere which is subducting at the subduction zone. So, it is cold because it is now away from the mid-oceanic ridge. Once upon a time it was formed at the mid-oceanic ridge, it was hot. Once it move away from this mid-oceanic ridge system, it becomes rigid, it is cool, its density increased. Then it becomes rigid and becomes fractured. Due to contraction, fractures were developed. Normal faults were developed at the mid-oceanic ridge system. And due to this fractured and normal fault, this water was circulating inside, and that is why it is altered to serpentinite. It is to green schist phases of metamorphism. Then part it will remain basalt, and it is sandwiched between a sediment layer at the top, that is layer 1 in the oceanic lithosphere, and the peridotic layer at the mantle, that is the layer 4 of the oceanic lithosphere, and descends into the asthenosphere at a variable speed and angle. So, the angle of subduction is different. It may be very shallow, for example, like here, and may be deep, for example, like here. And it is a variable speed. The rate of subduction, it varies, means there is a wide range of variation. So, that means this statement, it says everything about the subducting slab. Now, what happens? What next? If this is happening, this type of slab characteristics, it is going inside. What changes is taking place? How it is responding to this high temperature and pressure environment which is inside in the asthenosphere? So, the subducting lithosphere can retain its separate thermal and mechanical identity to a considerable depth until sufficient heat has been transferred to it from this mantle to increase its temperature to that of its surrounding. So, now if you see here, this is the subducting lithosphere which is going down, and this is the asthenospheric system. Now, once it is there, so heat from the surrounding asthenosphere will try to move in this direction and to this. That means, all side from the asthenosphere, heat will try to move towards the colder region. So, here we have a cold core, and gradually heat will be more here, and gradually it will reduce and reduce, and this is the least heat is here. Similarly, this side heat will increase at the surface and gradually decrease to this core. Now, if this is so, now you see how these thermal contours, this is the temperature contours. At the top surface, if you notice the temperature contours, they are very closely spaced, very closely spaced. However, at the bottom side, if you see these temperature contours, they are more or less uniformly spaced. So, what is the reason? The reason being, if you remember our earlier class when we are talking about the oceanic lithospheric system, we have layer 1 which was sediment and layer 2 which was below basalt. Then we have sheeted dike complex, then we have isotopic gabbro, then we have that is the layer gabbro, then we have peridotite. So, like this. So, now the same thing it is inclined here. So, that means I can take a slice which can represent here. So, that means here you see at the lower side that is the peridotite, the mantle peridotite, and here we have mantle, the asthenospheric system. So, compositionally this side and this side, that means here and here, this is more or less same, and mostly it is peridotite means we have rich in iron, rich in magnesium, manganese, like that. So, that means we have ferromagnesian content high in this side, and that is why there is a very high, that is very every region that heat can transfer through these ferromagnesian minerals easily, because they are good conductor of heat. So, that is why we have a uniform distribution of heat at the lower part of this lithosphere, which is peridotite in composition, and this is the mantle peridotite is here. So, that is why there is a uniform distribution of the contours. However, you are coming to this surface, at the surface mostly it is the sediment, quartz, feldspar, micas, like different sedimentary particles are there, sedimentary grains are there, and these are not of good conductors. So, that is why whatever the heat it is there, it is accumulating to the surface, very closely spaced contours, that is why it is representing, because heat transfer is not as simple as in the lower side. So, that is why heat accumulation is there. So, due to heat accumulation, the top surface is representing very closely spaced contours, however, the bottom is representing widely spaced contours. So, that means a plate which we are putting inside, it is responding to the temperature in indifferent manner. That means, lower part it is a different thermal structure and the upper part it has different thermal structure. Now, this is a simulation, that is the thermal structure of this mantle wedge and the subducting slab calculated from finite element modeling and the location of the initiation of vapor saturated melting, that is the partial melting taking place. If you see here, one set it is saying 20 millimeter per year subduction, and this is 40 millimeter per year subduction, 60 mm per year, and it is 100 mm per year. Similarly, if you see, the angle of subduction is also varying here. This is shallow angle and this angle of subduction is also varying. Now, what is happening here? If it is subducting at a lower rate, that means 20 millimeter per year, and the subduction angle is like this. So, now you see the vapor phase of melting, it is starting relatively at a shallow depth and it is occurring up to here. So, that means minimum 142.5 kilometer depth and maximum 195 kilometer depth. So, that means if the rate of subduction is slow, that means it is getting high time or longer time to exchange heat from the surrounding. So, that is why at the lower level, that means at a lower depth, so vapor melting is starting in the mantle. So, if I are increasing the rate of subduction, for example, we are shifting it from 20 millimeter per year to 40 millimeter per year. So, here it is happening, you see this is the minimum is 127.5 kilometer and it is 191 kilometer. That means the vapor melting, that is the partial melting due to dehydration of this mantle, it is occurring relatively at a shallow depth. And if it is 60 millimeter per year, so that means here it is like this, that means vapor melting is about 112.5 kilometer to 190 kilometer. And if the rate of subduction is high, very high rate of subduction, we are inserting this plate very rapid manner. So, that means we are not giving chance to heat transfer to this slab from the surrounding. So, that means no melting, no vapor melting is there. So, that means here there are different angle of subduction, then different rate of subduction is taken into account, and this finite element modeling was carried out, and this says that different rate of subduction, different angle of subduction, this vapor melting or the partial melting due to dehydration is occurring at different levels. And the factor controlling the temperature distribution are the rate of subduction first, as we are talking about. If the rate of subduction is slow, that means it is getting high time, that means higher time of interaction with the surrounding. So, that is why more rapid descent of the less time there is the absorption of heat from the surrounding and mantle by conduction. So, high rate of subduction, that means it is getting less time to interact, and low rate of subduction it is getting high time. And the age and the thickness of the descending slab, age of the oceanic lithosphere and the thickness of this oceanic lithosphere. The thicker the slab, the greater the time taken for it to equilibrate thermally with the surrounding asthenosphere, because we are inserting a more thick slab. That means less, it will take more time the heat from the surrounding to insert or to move inside this plate. And if it is a thin slab, so that means within very less time it will equilibrate with the temperature from the surrounding. And edge is that means the thickness is proportionate to edge. So, that is why more the edge and more the thickness, so we are getting more time to equilibrate with the surrounding, and the reverse is also true. Then frictional heating of this upper and the lower surface of the slab. So, as it descends down, so the slab is resisted by the asthenosphere. So, once it is resisting, so we have a frictional system here, we have a frictional system here. So, due to this frictional heat, so this heat is also transferred inside. So, that is why this it will take some time to equilibrate from the surrounding. Then the conduction of heat into this slab from this asthenosphere. So, we have a conduction process, we have a asthenosphere here, we have a asthenosphere here. So, heat is continuously being conducted inside. So, that it will try to equilibrate the surrounding and this inside of this plate. Then heat derived from the radioactive decay of these materials in the oceanic lithosphere is likely to be small, as the oceanic lithosphere are rarely or largely barren from the radioactive minerals. So, that means we know the radioactive minerals like uranium and thorium, potassium, they are mostly confined in the granitic or the felsic rocks, rather basaltic rocks. And some of these minerals, that is radioactive minerals, they are derived from the sediments, and mostly they are confined to the surface within the sedimentary layer. However, most part of this plate, descending plate, it is composed of pedrotitic and basalt and gabbro, which is devoid of any or very less amount of radioactive mineral is there. So, that is why this point it is unlikely. So, the heat generated by the radioactive decay of these minerals, it is very less contribution to this to the increasing of heat of the subducting slab. Then heat associated with the phase change, it is also playing a major role. If you remember earlier class, we were talking about at certain distance, at certain depth, the phase changes taking place. So, phase changes means olivine is converting to spinel. Similarly, we have spinel oxide transition around 670 kilometer depth, and olivine to spinel transition is about 400 kilometer depth, and these are exothermic reactions and this is endothermic reactions. So, either of this case there is a heat imbalance. So, that means this is creating heat. So, that is why the temperature inside the slab is increasing, and the length of this Benioff zone depends upon the depth to which the subducting oceanic lithosphere maintains its relatively cold core. So, how it is happening? So, above all these points we have discussed about the heat transfer. So, that means the heat is being transferred from the surrounding into this subducting slab, and the subducting slab, that is why gradually it decreases its rigidity, and similarly if you going down, the thickness of this plate is decreasing. So, that is why most of this heat transfer and to this from the surrounding into this plate, they are occurring at the tip of this plate, and gradually the rigidity is increasing towards the surface. So, that means the first it loses its rigidity at the top, and this is the this is the contours, you can say how it is losing its rigidity, and at the core it will be more rigid, and towards the surface it will be more rigid, and to the depth and at the periphery it becomes less rigid. So, downward deflection of this isotherm and hence the length of the seismic zone is proportional to both the rate of subduction and the square of its thickness of this lithosphere. So, that means if you see here, we have a lithospheric thickness which is proportional to the square root of its edge. So, that means here L length of this Benioff zone, it is proportional to R. R is the rate of subduction in millimeter per year, and this L it is proportional to T square. T is the thickness of the subducting plate in kilometer, and this thickness is proportionate to the square root of its edge. So, the edge in million years. So, we can combine these three equations into one. So, length of this Benioff zone it will be like this. So, this is constant. So, that means if we are putting these different values in this formula, for example, an oceanic plate having 200 million years age and subducting at 20 mm per year. So, this will have a Benioff zone around 400 kilometer. So, that means here if you see different Benioff zones, they are calculated, and this length of this Benioff zone is calculated at different places, different trend sites, and it is falling in this graph. So, that means we have a relationship between the length of the Benioff zone and the rate of subduction and the age of the oceanic lithosphere. So, as heat is transferred into the slab, temperature gradients are established such that the asthenosphere in the vicinity of the slab becomes cooler and more viscous. For example, if you see here, now heat is transferred from the surrounding into the plate. So, once the heat is transferred from the surrounding to the plate, gradually the temperature in this peripheral zone it is decreasing. Once the temperature at the peripheral zone is decreasing, this becomes more viscous. This side of this asthenosphere becomes more viscous. So, once it is more viscous, it will adhere to this downgoing plate. So, now this plate is downgoing. Along with this downgoing slab, some part of this asthenosphere which is losing heat or contributing heat for cooling this for heating this downgoing slab, it is also adhere to the system. So, that means the whole system is going down. So, thus more viscous asthenosphere is then dragged down with the slab, causing less viscous mantle to flow behind it. So, that is why this system is going down, and to compensate this area, now the less viscous material from this asthenosphere it is flowing to compensate this place. And most of this water carried to this great depth is confined by hydrous minerals, and it is altered and metamorphosed crust including serpentinite. So, now you see we have a surrounding asthenosphere which is going down, and it is surrounding by this subducting slab. So, that means now the water is released, and that water it is that means it is metamorphizing this mantle system. So, that means it altering the mantle system, it is the serpentinite. So, now we are putting serpentinite into deeper into the mantle system. So, this fast spreading ridges, there is a less chance that it will be highly serpentinized, but in the slow spreading ridges it is getting enough time to serpentinize itself, because it is slow spreading ridge, that means more interaction from this oceanic water and more water will ingress inside and it is coming. But if it is a fast spreading ridges, that means suddenly it is spreading and it is going down at a higher speed. So, there will be a less interaction with the surrounding water system. So, that is why the fast spreading ridges they are less serpentinized as compared to the slow spreading ridges. So, slow spreading crust it is known to contain some perhaps about 10 to 20% of that. So, with increasing pressure, hydro basalt and gabbro are metamorphosed progressively to blue schist, then amphibolite and eclogite phases, and which water is released inside. So, that means those water which is released from this system, that is able to partial melt the mantle, and once the partial melting of the mantle taking place, magma is generated, and that magma is coming out as island arc system or volcanic arc system, and volcanoes are formed. So, now it is the interaction of the downwelling mantle with the aqueous fluid rising from the sinking slab that thought to be produce partial melting in the mantle. And Ringwood 1977 suggested this partial melting takes place at a relatively low temperature because high water vapor pressure resulting from the dehydration of various mineral phases in the downgoing slabs. So, this water, it is acting as a primary agent that drives the partial melting beneath the arc. So, once it is partial melting is taking place at the mantle, this magma is generating, and here it is forming this volcanic system. So, what is the volcanoes and what is their product? What is the magmatic composition? How the composition varies with depth? How this composition varies with water content? How the composition varies with the amount of sediment present in the subducting slab? That will come under this subduction zone magmatism, that domain. And when the sufficient partial melting occurs, probably 10 plus minus 5% of the melt aggregates, and it begin to rise towards the base of the crust, and the magma moves into the crust and differentiate and mix with the surrounding, and that means it will mix with the surrounding country rock and mix with the magma which is generated at the difference level, and finally we are getting a magmatic arc. And magmatic arc, starting from this lower depth to higher depth, the magma composition varies. Depending on the amount of sediment, depending upon the amount of water is released, this magmatic composition varies. Depending upon the degree of partial melting of this mantle, the magmatic composition varies. So, all that will be taught in the domain, that is the plate tectonics and magmatism. So, thank you very much. We will meet in the next class.